Hello everyone. Today I'll be presenting on data augmentation strategies for sequential recommender systems. This approach aims to improve the performance of models that predict what a user might want next based on their previous interactions, particularly by handling issues like sparse data, cold stats, and imbalanced interactions. However, they face some common problems like sparse data, cold stat problem, and data imbalance. Many users interact with only a small fraction of available items, and new users or items don't have enough historical data for accurate predictions, and a few users or items dominate the data, leading to biased results. To address these challenges, data augmentation offers a creative solution by artificially modifying existing data in meaningful ways. We can improve the diversity and quality of training data, enabling models to learn better patterns. In this study, we explored different augmentation strategies applied to the SAS-REC model, a transformer-based sequential recommendation algorithm. Our primary goals in this study were to explore and apply a range of data augmentation techniques to sequential recommendation systems to test how these strategies impact the SAS-REC model's performance, to evaluate the model with and without augmentation and understand the improvement, and to explore other models to get a comprehensive view of augmentation's effectiveness. This systematic approach helps us identify the best strategies for real world applications. We used three well-known datasets: Movie Lens 100K, Amazon Games, and Govella. Movie Lens 100K is a popular dataset containing movie ratings from users, whereas Amazon Games is a dataset of user interactions with gaming products, and Govella is a social network dataset where users checked into different locations. Since these datasets are quite large, we sampled 10% of the data for faster training. This also ensured that our experiments remained computationally feasible while retaining the temporal order of user interactions. To evaluate the effectiveness of data augmentation, we used SAS-REC, a state-of-the-art sequential recommendation model based on the transformer architecture. SAS-REC is particularly strong at capturing sequential patterns because of its self-attention mechanism. It has the three main components: embedding layer, multi-head attention, and dense layer. Embedding layer transforms item IDs and their positions into meaningful vectors, whereas multi-head attention captures relationships between items at different positions in a sequence, and dense layer predicts the next likely item in the sequence. For our experiments, we used hyperparameters like an embedding dimension of 64, two attention heads, and a dropout rate of 0.2. These were chosen to balance computational cost and model performance. Now let's look at the data augmentation strategies we explored. These strategies manipulate user interaction sequences to create additional training data like shuffling, substitution, cropping, masking, repeat, and mix. Shuffling rearranges items in a sequence while preserving the overall timeline. Substitution replaces some items with others either randomly or based on similarity. Cropping tourniquets sequences to simulate missing data, making the model more robust. Masking hides certain items and asks the model to predict them. Repeat duplicates certain items in sequences to emphasize their importance. Mix combines items from multiple sequences to create new interaction patterns. By using these methods, we generated diverse data for training, which helped improve the model's learning ability. Let's now focus on the results, which show the impact of data augmentation on SAS-REC model's performance. This is where the real value of our exploration becomes clear. Before applying any augmentation, we trained the SAS-REC model on the original datasets to establish a baseline. The model's performance measured using hit ratio of k, HR at the rate k, and normalized discounted cumulative gain at k, that is NDCG at the rate k, was moderate. Here's a breakdown. Movie lens is HR at the rate K was 0.45, meaning the correct item appealed in the top 10 recommendations 45% of the time, and NDCG at the rate K was 0.30, indicating room for improvement in ranking accuracy. Whereas in Amazon games, HR at the rate K at the rate 10 was 0.42 and NDCG at the rate 10 was 0.28, showing similar limitations in capturing user preferences. Govella shows that HR at the rate 10 was 0.38 and NDCG at the rate 10 was 0.25, the lowest among the datasets, highlighting the challenge posed by sparse and imbalanced data. These results confirm that while SIS-REC is effective, it struggles with challenges like sparsity and cold starts, particularly on datasets with fewer interactions or more complex patterns. Performance after data augmentation. Applying augmentation strategies led to significant improvements. Each strategy targeted different challenges in the data, and their impact varied slightly across datasets. Let's analyze them in detail. Firstly, masking. This strategy consistently yielded the highest gains. On Govella, accuracy improved by 6% from 85.2% baseline to 88.2%, and test loss dropped significantly from 0.35 to 0.28. On movie lens, accuracy improved by 4% from 80.3 to 82.2%. Masking likely performed best because it forces the model to predict masked items, enhancing its ability to generalize from incomplete data. Whereas in substitution items improved the model's ability to handle variability in user interactions. Accuracy on Govella improved by 15% and test loss dropped by 0.35 to 0.32. On Amazon games, accuracy increased from 83% to 83.5%. Substitution mimics the real world scenario where users might replace an interaction with something similar, helping the model learn diverse patterns. Whereas in shuffling items in sequences improved accuracy by 3 to 4% across the datasets. For instance, on movie lens, accuracy increased from 80.3% to 81.5%, and test loss reduced slightly. This strategy enhances the model's robustness by training it on slightly altered sequences without breaking temporal dependencies. Whereas in mixing items from different sequences gave the most dramatic improvements on some datasets. On Govella, accuracy improved by 7%, the highest overall gain. This strategy effectively exposes the model to interactions across users, enabling it to capture patterns that wouldn't be apparent in a single sequence. Whereas in cropping, while not as impactful as masking or mixing, cropping still improved performance, particularly by making the model robust to incomplete sequences. For example, on movie lens, accuracy improved by 1% and test loss reduced slightly. In repeating items within the sequences had a moderate impact, with accuracy improvements of 2 to 3% across the datasets. This strategy reinforces certain interactions, helping the model prioritize frequent patterns. Performance comparison across the datasets. The impact of augmentation strategies varied across the datasets. For instance, on movie lens, masking and substitution yielded the best results, with masking improving accuracy by 4%. On Amazon games, mixing and substitution stood out, likely because the dataset gaming interactions benefited from more diverse sequences. On Govella, masking and mixing gave the highest gains, reflecting the effectiveness of these techniques on sparse, location based interactions. The diversity in results highlights how augmentation needs to be tailored to the dataset's characteristics. For datasets with sparse or highly variable interactions, strategies like masking and mixing are particularly effective. While augmentation significantly improved performance, it also introduces some trade offs. Strategies like masking and mixing required additional pre-processing, increasing training times by 10 to 20%. For example, training time on Govella increased from 2.5 hours to 3 hours when using masking. This trade-off is important to consider in real-world applications where computational resources may be limited. Overall, these results demonstrate a clear benefit from augmentation, with notable accuracy gains and reductions in test loss. The added computational cost is justified by improving ability of the model to generalize and handle complex patterns. We can see that masking is the most effective individual strategy, particularly for sparse data like Govella. Combining strategies such as mixing sequences can yield even higher improvements, especially in datasets with complex patterns. Augmentation improves both accuracy and model stability, but it comes with computational overhead. By emphasizing these insights, we can see how augmentation transforms a model's ability to predict user preferences effectively even under challenging conditions. We didn't stop at SIS-REC. To benchmark performance, we tested other models like GRU4REC and Kaiser. While these models are effective, SIS-REC generally outperformed them because its self-attention mechanism captures long-term dependencies better than recurrent or convolutional architectures. Despite the improvements, the study faced some challenges: large dataset processing and computational complexity and cold stack problem. In large dataset processing, even after sampling, datasets like Govella required significant time for training, whereas in computational complexity, applying multiple augmentations together increases the processing overhead. While augmentation mitigated some issues, it couldn't fully solve the lack of data for new users or items. These limitations reminded us that there's room for further optimization. To conclude, data augmentation is a powerful tool for improving sequential recommendation systems, with strategies like masking and mixing providing to most the most significant gains. These techniques increase data diversity, allowing models to generalize better. We could explore advanced augmentations like adversarial training or back translation. Real time augmentation during training could help models adapt dynamically to user behavior. Testing with other architectures like BERT4REC could deepen our understanding of augmentation's impact. Thank you.